Hello, this is lesson 2 of unit 2 of the physics section of the big data applications and analytics class. And we get started on event counting here. Um, so if you look at a lot of data analysis, it consists of setting up a process that gives you events. I mean, the obvious example are sort of surveys. When you have a political election, there are lots of surveys. Well, there are always lots of surveys, but political elections focus attention on surveys, and you count the number of people who feel in a certain way about the qualities of different individuals or different parties and so on. Alternatively, you can take some data, you build some software, that software assigns, say, a feature to the data that is good or bad, or it's big or little, and the result of that characterization for each of your data is an event. Another obvious sort of scientific or technical source of events is sensor nets, where the event is the result of a sensor measurement. And if you like, sensors are an example of a device that streams events. Typically, and at least in the view of this class, they stream the event back to the cloud. Sometimes results are yes, no. They can, of course, be totally different. They can be red or blue, or in the case of the physics, they can be this is a pi meson of such and such momentum and such direction, and the quality of the of our understanding of this particle is X%. But sometimes they're just yes nos. Did the person vote for candidate X or not? Did the event fall into a certain bin of the histogram or not? Um, so so when you have histograms, when you put things in bins, you're actually giving a yes/no decision for each bin. Although actually what you're looking at is a value. So it could be the mass of the prototypical Higgs particle. That mass is you look at its value, say between 100 and 140 GeV, and you stick it in a bin, and then you get this enhancement around 125 GeV. So the decision about which bin to put it in is yes, no. The thing you're actually histogramming is and the real value of the event is a real number, the mass of the Higgs particle. So here we have our first Python, which is simulating the what experiment might see. We have to use NumPy. We want to have matplotlib to plot it. We need some random numbers because we're using Monte Carlo. We're generating a random number between 110 and 140. That's this thing here. My base starts with 110. That's 30 times the default random number, which is uniform between 0 and 1. We actually don't want uniform between 100. This will give you numbers uniform between 110 and 140. You actually want them having an excess of events at the low values and less at the high values. That is ingeniously done by this index command, which is called accept reject. We will discuss accept reject later on in the class. Then we actually want a nice Gaussian, which is going to be the Higgs. That's done here. This generates you 300 Gaussian events. This is the Higgs peak. And this thing here is the background. This thing here is the signal plus the background. This thing here is what happens if you measure the Higgs more accurately. The observed width is not due to the physics of the Higgs decay. It's actually due to the measurement error. So when you look at a particle, which I mentioned in the last unit, was actually this sort of bump. That bump has a width consisting of two components, which depends on the particle, which component is bigger. In the case of the Higgs, the measurement error dominates the width of the particle. In the case of other particles, actually the physics width of the fact that the particle decays dominates. And we here generate what would happen if you built a more expensive experimental apparatus and measured it more accurately, which would require you to do a more accurate measurement. In this case here was a 2-photon final state. You'd have to measure the energy of those photons more accurately and or their direction more accurately. Then you could get a narrower result. Notice this has the same number of events, I just measured more accurate. Here we have the same thing in Java. And you can see, as I pointed out, it's decidedly more voluminous. It is doing the same thing. Here's the random number generator. Here's this base here. And here we do the equivalent of accept reject, which was done in a very cunning, obscure single line in Python. One of the problems, of course, of Python is, and that's actually particularly clear in this example here, the Python commands highly non-opaque. And the advantage of the Java is that even though it takes order of magnitude more lines to describe, it's actually rather clearer what it does. And so if you actually want to understand the accept reject method, which is summarized in this statement here, is much clearer, I think, from the Java than it is from the Python. Because, at least for me, I mean, now I understand accept reject and I understand the Java very well. For me to know that the right way to do it is what I did for Python, I have to sort of study the rather enigmatic Python documentation. And here we have all these exactly the same arrays: the sloping array, the Gauss array, the narrow Gauss array, and the total. And here we have these two totals. Now we actually use this software to count events. Thank you.